does actually. They're doing its own recording, I think. So now it's recording. Yep. All right. So this is, I guess, the best part of the course: singular value decomposition. Gilbert's rank calls it the pinnacle or climax of a linear algebra course, and for a good reason. It's probably the most powerful theorem in linear algebra. If you only want to remember one theorem, then remember the singular value decomposition theorem. And it's useful because it's so general. So let me first motivate it a little bit. So before we talked about eigenvectors and eigenvalues, which are an incredibly important concept, right? We discussed that they have like lots of applications. You did the differential equations, there was this Markov chains, and many other applications. So this is the definition of eigenvalue and eigenvector. But we have also seen that they have a lot of limitations, right? What are some of the limitations of eigenvalues and eigenvectors? They don't always work, right? What are some of the reasons why they don't work? Well, one problem is I have to assume something about A at the first place, right? A have to be square. If A is rectangular, then this doesn't apply, period. That's one problem. But even if A is square, then we still have some problems with the eigenvalues and eigenvectors, right? Of two types. Does someone want to say it? I just keep saying it over and over again. I'm sure you guys know it, so don't be shy. So one of the problems is sometimes we have to go to complex domain, right? That we are, even if the matrix was real to begin with, sometimes we need to use complex eigenvalues and complex eigenvectors so that we are able to find enough of them. And sometimes even if we do that, we still are not able to find enough of them. Sometimes some matrices are simply defective, that they don't really have an eigendecomposition. In other words, not all matrices can be written in this form, right? So sometimes you can do it. For example, for all symmetric matrices, you can do it, right? But that's adding additional assumptions on A. So chances are you have a matrix which just does not meet these assumptions. If it's rectangular to begin with, then this does not directly apply. It will apply through single value decomposition. So this basically means that not all matrices are diagonalizable. Or I guess in general, I could just say that this is some matrix V and V inverse, right? Wouldn't have to be orthonormal. But even that does not save us. So what will save us is the concept of singular vectors. Singular vectors and corresponding singular values. And these guys magically solve all these problems. So you can see single vector, single values, it refers to like similar ideas as eigenvalues and eigenvectors. And the point is that these single vectors and single values, they will work for an arbitrary, absolutely arbitrary matrix. It can be rectangular, can be whatever. It would also work for a complex matrix, but we will be dealing only with real matrices. And these problems always, the problems with eigenvectors go away. We don't need any complex single vectors and singular values. They will be just real and nice. And the trick is to use two sets of singular vectors. Sometimes they are called left and right singular vectors. So the property of single vectors and single values is this. So if I have an arbitrary matrix A, then I say that V1 is a right singular vector and U1 is a left singular vector and sigma 1 is a singular value. So sigma 1 is just a scalar and V1 is a vector from R to N and U1 is a vector from R to M. Okay. So maybe I'll repeat it in case you came late so we are not completely lost. I'm explaining what are singular values and singular vectors for an arbitrary matrix. It can be absolutely arbitrary. I'm assuming a rectangular matrix. And singular vectors come in pairs. There's like a right singular vector and left singular vector, and they are coupled through this equation. So if I multiply the right singular vector with my matrix, I get the corresponding left singular vector times the singular value. So notice that it's really the same idea as with eigenvectors, except that I essentially like split this x-axis in like two different copies, if you want to look at it this way. So here I have v, and u, and those are different vectors. Already the dimensions are different, right? v1 is n vector and u1 is m dimensional vector. And the idea of the singular value is sort of analogous to the idea of eigenvalue there. So this would be one, and of course we can have more. We can have another singular vector, or right singular vector, another singular value, and another left singular vector. The singular values can be always chosen so they are non-negative. All singular values can be set to be non-negative. That's the usual convention there. So in general, I can continue. How far do you think I can continue? Then I would get a third one, fourth one. How many do you think I will be able to find for a general matrix? What would be your bet? It's an m by n matrix, right? Can be anything. Can be singular. Yeah. Yeah, that's correct. Yeah, so I can continue up to the R, where R is the rank. So let's say that rank of A is R. Well, you will see later that I can actually continue even beyond that, but then it becomes, I should probably say that these guys are positive. R is the rank, and then I can still continue. I will explain that later, then it will make a little more sense. I can still continue, but then the singular values will be zeros. So that's a slightly special case. Let's focus on this basic case first. So all these v1, v2, and so on to vr are vectors from Rn, and we can say even more. They are in fact vectors from the row space of A, or the column space of A transpose. Because I am not that idealistic that you would be remembering these things, I will recap them in a little bit on the next slides, but let me first finish this. Similarly, the left singular vectors are actually from, guess what, the column space of A, right? Which is a subspace of R to M. I guess would have been nice if I wrote it like this. It's a subspace of R to N. And there is a symmetric relationship. So if I wrote this in general as AVI equals sigma I UI, then there is a symmetric relationship which tells me for AT, it says that AT maps the vectors the other way around. It maps the left ones via the single value to the right ones. So from this you can clearly see that the UI vectors are in the column space, and if you remember the definition, and the VI's are in the row space, or column span and row span. So actually let me recap these notions in case you don't. It's been a while since we had those. So this is what is a column span. So this was, remember, the cool thing about SVD is we'll tie in together many of the concepts we talked about before. So now I need to review if you remember, we were talking about the 4 fundamental subspaces of a matrix. And that's what we will that's what SVD directly exposes. Single value decomposition is often abbreviated just as SVD, so I'm just using SVD for short. So the SVD will tie in the 4 fundamental subspaces with the notion of orthogonality, orthonormality, and eigenvectors and eigenvalues, they will also naturally appear there. So this is really like the top of the mountain, if you will. Sort of cool that there is like one theorem that explains a lot. So the column span is a very simple concept. We know it's an example of a subspace, right? That's a subspace of R2M. So the matrix is like this. If I said that n is greater than m, if it's more columns than rows, they're not just all linear combinations of all the column vectors, right? That's what this AX says. So all vectors y, which can be formed as some linear combination of the columns of A. Right? We have discussed that before. Do you remember what is the row span then? Before I show the next slide. Yes.
Use the rows for a basis.
Correct. And the nice thing is that I can actually also explain it. As I define column span, I can just say it's column span of A transpose, right? Because you know the transposition, basically rows map to columns and columns map to rows. So the transposition exchanges the role of rows and columns. So the row span is the subspace given by all linear combinations of the rows of the matrix. Okay. Do you still remember what was the null space? I hope so. So let's just do it quickly. So null space is the set of all vectors which the matrix maps to 0. Okay. For all of them, it's very easy to show that's vector subspace, right? We discussed this. You should be able to show it yourselves at an exam or something like that. There was also the concept of left null space. Do you remember what was a left null space? There need to be 4 of them, right? So we have the row space, column space, null space, and left null space is the 4th piece of the puzzle as the matrix decomposes in this puzzle. Do you remember what was the left null space? Yeah.
E transpose A.
Huh?
Is it under E transpose A?
Yeah,
the null space of the transpose A.
Yeah, that's correct. Yeah, left null space is the NAT. So what does that mean? That means all vectors y such that ATY is 0, right? For y from R to M, because I transposed it. But this I can also look at it as YTA, right? That's y left. If I multiply the matrix with the vector from the left, I go to 0. Okay, so those are my 4 fundamental subspaces, and remember this beautiful diagram we discussed quite a few weeks ago, right? It's been a while, but now it comes back, and now we'll actually be able to find orthonormal bases in all of these spaces, and that's essentially the idea of SVD. So let's remember this. I also had to recall it. I was actually watching my lecture like 1.5 speed. It's sort of funny. I don't know if you tried watching it like with higher speed, the lectures. So the idea is if I have a space R2N on the left and R2M on the right, so and I have a matrix which is an R which way? M by N, right? Yeah, so it goes, so this way goes A, and this way goes A transpose, right? A maps from R to N to R2. I could write also like this. A maps from R to N to R to M. It consumes an N vector and produces an M vector. And A transpose, well, it has to go the other way, right? Because it's N by M matrix to Rn. And what is going on here is that here I am doing an orthogonal decomposition of the R to N space, that's here, and here I'm doing an orthogonal decomposition of the R to M space. So the input space of A splits orthogonally into these 2 components, the null space of A and the row space of A. or the column space of A transpose. That's the same. That's the same thing. Similarly, the R2M space, the image space of A, it splits into the left null space and the column space. And what I mean by splits orthogonally, it means that if I pick any vector here, it will be orthogonal to any vector here. I mean, this drawing is just like illustrative. Those are like not really orthogonal in 2D, right? But this is just like sort of like visualization. those are higher dimensional subspaces, right? In particular, what are dimensions, right? The dimensions of the row space and the column space are the same, and they are both dimension R, where R is the rank of A. And these are just the orthogonal complements of them. Remember, we were like discussing the reasons why they are orthogonal complements. So this is n-dimensional space, so the remaining dimension, there is n minus r remaining basis vectors, and here I have m minus r, so that these things really altogether generate R2m and R2n. To get someone. So the idea is that all the vectors from the null space, they map to 0. Here is a 0. They map to 0 here. Similarly, the AT maps all vectors from here to 0 here, right? And all vectors in the row space map to some non-zero vector in the column space, and the other way around. All non-zero vectors in the column space map to a non-zero vector in the row space. So one way you can look at it is that in every m by n matrix, there is an R by R invertible matrix waiting to break free. Or like that's like the real meat of the transformation, and the rest is sort of the padding that just like explains the singular parts, the ones that go to 0, one way or the other. Here is, actually let's do this. Here is a summary of that, what I was just explaining on that image, on the picture. So let's just go through that quickly. I think I covered everything there, right? So let's see. So those are the 4 fundamental subspaces: column space, null space of AT, column. So this is the row space. This is with the left null space and the null space. And right, ultimately A is mapping an R-dimensional subspace of R2n to an R-dimensional subspace of R2m. That's important. That's sort of also like the heart in the SVD. What do you think? Let's see if you already have some intuition about it. What do you think it means in terms of the singular values? I was previously saying that I was making this mess about greater than 0 or greater or equal than 0, right? So now you can probably guess that these guys from this R dimensional subspace that goes these non-degenerate vectors, or how should I explain? The vectors from this R-dimensional subspace that maps, and the vectors from the row space that map n to the column space and are not 0. They map in one-to-one manner. What do you think their single values will be like? Okay, maybe it's too early. Those are they will be corresponding to the non-zero, to the strictly positive singular values. Because the point is that this is invertible. It means that the non-zero vector from this subspace must go to a non-zero vector in the other subspace in a one-to-one manner. The one-to-one really means is equivalent to saying I can invert it, I can go back. It's not like 2 would be going to the same thing, because if 2 different things were mapped to the same thing, then there is no way I can invert it, right? Because I have some confusion there. That's the problem with the 0, right? With the vectors in the left null space, they go all to 0. There's no way I can invert it unless I like split the 0 into many different zeros, which is not possible. And that's what's written here. The vectors in null space go to 0 via A, and the vectors in the left null space go to 0 via A transpose. Okay. So now I think would be a good time to look back at this. So let's look at these defining. This is the equation we want the singular vectors and single values to satisfy, or right singular vectors and left singular vectors satisfy together with the singular values, right? And I have those equations from I going from 1 to R. So I can write this in matrix form like this. So here is my A, and I can put all these vectors V, there is R of them, into a matrix. And equivalently, I can put all these, or similarly, I can put all the U's into another matrix. So this just means multiply every column of this matrix by A. And the multiplication by sigmas I can accomplish simply by saying there is a diagonal matrix which looks like this. And there are zeros everywhere else. Diagonal matrix. Because this simply says multiply the first column by sigma 1, the second column by sigma 2, and so on, the last one by sigma r, right? So this matrix equality captures all these equalities in one, right? Might be interesting to take a look what is the dimension of this matrix. What is the dimension of this matrix? You tell me. So A was m by n to begin with, right? So what is going to be the dimension of this one? N by r. If I heard n by r, then I heard correctly. What about this one? Use r vectors in r to m, right? And I have r of them, so this m rows and r columns. And this is a diagonal matrix, so this is an r by r matrix. It's always good to make the check that the dimensions really match, because if the sizes of the dimensions of the matrix don't match, then there must be some mistake somewhere. So this is like the heart of the matrix. This is the r by r component there in the four fundamental subspaces. This is this non-degenerate part. Those are the non-zero guys from the row space that get mapped to non-zero guys in the column space, and the other way around, because these guys are exactly the basis of the row space, and these are exactly the basis of the column space. And actually the invertible, so those are like the bases, and the invertible part, that's this, all these sigmas. So here I have that sigma 1 up to sigma r are actually strictly positive. That corresponds to the fact that this matrix is invertible, right? If I had there 1 0, I would not be able to invert it, but there are no zeros. Okay, the main point of SVD is that we can actually find these bases such that all these vectors v1 to vr as well as u1 to ur are all orthonormal. I mean, these guys are orthonormal and these guys are orthonormal. Let me write it down. It is possible to find the vectors in such a way that v1 to vr are orthonormal. And the same thing is true for u1 to ur. In matrix language, how would I say it? If I said this is a matrix capital V and this is a matrix capital U, what would I say about the matrices V and U? I would just say that they have orthonormal columns, right? I cannot really say that they are orthonormal because they are not square. So those are so we can actually find these V and U matrices. Let me just call them V and U, which are orthonormal bases for the row span and column span. So even more is true. This is an orthonormal basis of C18, and this is an orthonormal basis of CA, of the column span and the row span. Now this is the meat of the matrix, but then there is more to it, and that more that might sometimes be quite important. So let me try to draw a little image. Let's assume that the matrix looks like this, that it's like this short but fat matrix. So it's an m by n, and I will just assume that n is greater than m. It would work pretty similarly for the other case when it was a tall and skinny matrix, but let's just consider this one. And if it's rank r, then I have this r bar I. Well, this is like conceptual. This is not a submatrix. The r is the rank of the matrix, so r is smaller than both m and n. So what we have so far, what do we have so far? Let me just take this matrix equality and let me show it graphically what it means, because I think that's a little bit nicer to look at it that way. So this is my A. This is my A. It's m by n. And I have the V, which is n, so this will be the same length, and this is r. So this is n by r. That's my V matrix with orthonormal, or let me give it V tilde, because I will define a better V in a second. And I have a U, just like this. So remember, the U is m by r, where m is the number of rows of A and r is the rank. U tilde. And here is what? Here is an r by r matrix, so it looks like this. That's the sigma matrix, r by r, right? And the dimensions m by n, and this is m by r, it's m by r, so I'm happy, this works. So far this only considers the basis for the row space and column space, right? And you can be wondering, what about these null spaces? I can build the null spaces into this matrix picture relatively easily. So look at NA. That is dimension n minus r subspace, and it's a subspace of R to n. It turns out that we can find, and I will explain how, but later. First I'm explaining how it works, then I will explain why it works. So those will be vectors Vr plus 1 to Vn. Of course they are from R to n, such that if I add them to the first V's, so the columns of my V tilde, then the complete sequence V1 to Vn will be orthonormal. So this is in general true. If I have some basis, I can always find an orthonormal complement of that basis to the entire space or subspace. Did we have that? Now I can't remember. I would hope we did, because it's like a basic thing in linear algebra. If you have some subspace, then I can really find an orthonormal complement to extend it to the entire space. So the same thing is true for the left null space. The left null space has dimension m minus r. It's a subspace of Rm. And here we can find u r plus 1, u r plus 2, and so on up to um, of course from Rm, such that, guess what, u1, if I put them all together, so if I take the columns of u, this is u1, this is u2, and so on, if I put them all together, I get again orthonormal basis. So if I put it here in the matrix picture, I can now expand that picture This is my A, which was m by n. Here was my original V. This was my original V tilde actually. And now I'm gonna expand it. Now I'm gonna take all these guys, Vr plus 1 to Vn. And notice that this was n by r, and now it's going to be n by n because I added the n minus r column vectors here. So this is going to be the full V. We put it here. This is what I had there before. That was the n by r, and this is the n by n minus r. So I took these column vectors and just put them here, like this. Now the same thing happens to u. So this was my original u tilde. And here I take the ur plus 1, that's going to be this guy, and all this way to um. Notice that it again becomes square, so this was n by n, this will be m by m. This is the m by r part, and this is m by m minus r part. And here I will do this. I will just extend the original sigma. Here is my original sigma. Here. And I just extend it by zeros. There is just a chunk of zeros. The sigma is the diagonal matrix, right? Remember that sigma is this is sigma 1 to sigma r. Like this. And this is an m by n matrix. Always check the dimensions. This is m by n, this is m by n. Good. And this is almost SVD. We just need one more step to get to the classical SVD form. All we need to realize here that now V is square and orthonormal, right? Before we only had that these columns were orthonormal columns, but now we complemented them to the basis of the entire space R to n. So this is a perfect square orthonormal matrix. That means that the inverse of V is what? Did I get you by surprise? V transpose, exactly. So that means if I write, so this is U and this is, oh, you know what? I will give this sigma tilde, and I will call this matrix just sigma. So this equation I can write as AV equals U sigma. This whole thing is sigma. This whole thing is V. This whole thing is U. This was my original A. Well, then the last step I need to do here is just multiply by the inverse of V, aka Vt, and I will get U sigma V transpose, right? Because I hit it with Vt from the right. Vt is V inverse, so this V disappears. It just becomes identity, and I get the V transpose on the other side. And check the dimensions, can't hurt. This is m by n. This U was n by n. This was, oh wait, this was m by m. This was m by n. That's the only rectangle there. And the V transpose, it's still n by n. So the dimensions work. And this thing is the singular value decomposition of A. This is SVD. So don't think that SVD are matrices. U sigma VR are matrices. SVD is just acronyms for singular value decomposition. There are some flavors of SVD. This would be called like full SVD. In some flavors, like you can notice that these zeros are basically not necessary there. That you can just kill the corresponding part there, and you can like talk about reduced or truncated SVD. But those are just like flavors of SVD. This is the main idea, and then you can like twist it in any way you want. Okay, so far I presented the idea what the SVD decomposition is, right? What I still owe you is to explain why this is always possible to find the SVD decomposition for any rectangular matrix, and how to actually find it. or what are the v and u vectors going to be. In particular, what are how to find r, the r where r being the rank, r vectors v and r vectors u, such that these equations are true. Okay, any questions so far? Good. So what I'm planning to do next is to do to start with a simpler example, my favorite 2x2 case. The 2x2 case is cool because it's simple, but you already get to see the idea. And actually most of these things will directly translate to n by n. Don't worry, I will do a general case properly too. I want to go over this relatively slowly because it's very important, so I'd like you to understand it as well as possible. So let's take this example. Rank will be 2, so let's assume it's full rank, so that also means that A is invertible. But it doesn't have to be symmetric. If it was symmetric, we would be fine. The eigen decomposition would already work. But let's say it's arbitrary, except for it's invertible in full rank. So if we want to find SVD of this matrix, what we need to do is to find the V1 and V2 and U1 and U2 such that AV1 and sigma 1, sigma 2, such that AV1 will be sigma 1 U1 and AV2 will be sigma 2 U2, right? Now this is all simple because they are all just 2x1 vectors, and those are just scalars. And what I want is that V1 is orthogonal to V2 and U1 is orthogonal to U2. Right? I was saying that I want these matrices to be orthonormal. So the main problem, so the task basically is to find V1 and V2 such that V1 is orthogonal to V2, and so this would be simple, right? In the plane you can like give me tons of vectors that are orthogonal to each other, right? But the catch is that I have another condition, that I want that AV1 is also orthogonal to AV2. That's the tricky part. Because if I do this, then I can just take U1 being AV1 divided by the norm of AV1, and U2 being AV2 divided by the norm of AV2. And these norms thus will be exactly the single value. So sigma 1 will be norm of AV1 and sigma 2 will be the norm of AV2. And then if I manage to do this, then I will just define my V matrix as V1, V2. It's 2x2 matrix, right? It's sort of simple here. And U is U1 and U2. And of course sigma is just sigma 1, 0, 0, sigma 2. And I know that AV is U sigma, because that's how I created them, right? I said that my U's are exactly AV's divided by the length, where I defined that the sigma is the length. And because V is orthonormal, then I can write it this way, that A is U sigma VT. So the question is, how do I find such vectors V, so that they are orthogonal and their images by A are also orthogonal? So like you can look at it graphically. Like if I start, so the matrix maps R2 to R2, right? So I need to find two vectors which have like 90-degree angle, such that after the mapping by A, let me show it like this. I get different two vectors which are again orthogonal. That's the tricky part, right? I could trivially pick any two orthogonal vectors here. I could just pick these two. That's easy. But then, more likely than not, after the mapping, they would not be orthogonal anymore. So how can I find them? Here is the critical trick. The critical trick is to take ATA. Because if I take ATA, what happens to the SVD? What happens is U sigma PT transpose U sigma PT, which is B sigma transpose UT U sigma VT. We know that U is orthonormal, so this is identity. And because sigma is diagonal, this is just sigma squared, right? Because sigma transpose is just sigma. And so sigma times sigma is sigma squared. The sigma is a diagonal matrix here. So sigma squared, how does sigma squared look like? It's just sigma 1 squared, 0, 0, and sigma 2 squared. So if I compute the ATA, then I'm looking only for this type of decomposition. The cool thing is that the U's disappeared, right? That was, I guess, the complication with SVD, that I have these two pairs of vectors. I have the left and right single vectors, right? By taking ATA, the U disappears, and I am only solving for the V's. So how do you think I can find these V's? That's the key thing here. So key, it's worth thinking about it for a little bit. So my A is given, right? And I'm looking for V's and sigmas that satisfy this matrix equation. In other words, I'm decomposing ATA. We have seen something like that before, right? Don't be shy to say it. So first of all, we can notice something about ATA. ATA certainly is symmetric, right? Because I've done it many times. I can do it one more time. This is just AT, and this is A twice transpose. That's just A. That is symmetric. ATA, we also discussed before, it's positive semi-definite always. And because we assume that A is invertible, then ATA must be positive definite. Right? Does it ring a bell? Oh well. It means that I can just now do eigendecomposition of ATA. Because it's a real symmetric matrix, so I can just do eigenvector decomposition. You know that in the case of a real symmetric matrix, I can find eigenvectors which are orthogonal, and because it's positive definite, the eigenvalues will be positive. Isn't that cool? So this, I can find this decomposition exactly using eigendecomposition. So in other words, eigenvectors of ATA give me V. And eigenvalues, if I have eigenvalues of ATA, let's call them lambda 1 and lambda 2, then how do I set sigma 1 and sigma 2? Nobody? All I need to do is take the square root of lambda 1 and lambda 2. Because I assume because I know the matrix is positive definite, then the lambda 1 and lambda 2 are all positive, both are positive, so I can take the square root, and it stays real. And these are my singular values. That's just because here I'm taking sigma squared, right? So if I square them, I get there exactly the lambda 1 and lambda 2, the original ones. So the eigen decomposition works. So this is how I can find the right singular vectors and the singular values in this specific case. If I have this, how do I find the left singular values? Left singular vectors. There are no left and right singular values, only the vectors are left and right. The singular values are the same on both sides. So how do you think I find the u? So I already found the sigma and v, right? Or maybe from here it's better. I have a, v, and sigma. I know that the sigma is invertible because I assume that those are positive. So all I have to do is take a, v, sigma inverse. Because sigma is invertible diagonal matrix. I just invert the singular values. There's another way how I could find the left singular vectors. Do you see that way? Here I took ATA, right? What would happen if I took AAT? AAT is also symmetric, positive semi-definite, in this case positive definite, because I assume that A is invertible. And if I take eigenvectors of this matrix, and they will exist, they will be real, they will have eigenvalues which are positive, and they will be orthogonal, so they will form exactly the left singular vectors. I guess you can look at it this way, that AAT is u sigma vt times u sigma vt transpose, which is just u sigma vt v sigma transpose u transpose, which is nothing but u sigma squared ut, right? So this is just eigen decomposition of AAT, reveals the left singular vectors and again the singular values. They must be the same, singular values. Okay, so I hope I confused you enough. Next time I will try to do an example for this 2x2 case, which I think it makes it a little bit more intuitive when you see the actual numbers there. A little bit more intuitive. Don't worry, I will explain it once again for the case of a general matrix, for an m by n matrix. The idea is going to be pretty much the same, with like a few more nuances there. Okay, so do you have any questions at this point? If you have questions at a later point, that's fine too. You can always ask. Okay, so thank you.